So now in the second part of the lasso regression in R tutorial, and this is really a continuation of part one of lasso regression in R, I'm going to show you how you can compare how a lasso regression model that you trained using k-fold cross-validation compares to an ordinary least squares linear regression model, so a conventional linear regression model, in terms of predictive accuracy and performance. Now, in order to get caught up on where we are here in this tutorial, be sure that you've already watched part one of the lasso regression in R tutorial. And as you can see here, we've already got some script laid out here, as well as a number of objects in our global environment, some of which we're going to be referencing here moving forward. So I'll make a quick note here that we are moving on to, we are going to compare an OLS multiple linear regression model to lasso regression, okay, that we've created here. Now, I'm going to show you how to assess the performance of an ordinary least squares multiple linear regression model using k-fold cross-validation. So in other words, to try to anticipate how well this model is going to perform with future data based on how well it performed in the k-fold cross-validation process, which is usually a better indicator than just using the r squared or the adjusted r squared from the standard OLS linear regression estimates. But I'll show you how we're really getting to the same model at the end of the day when it comes to the OLS multiple linear regression model. Okay, so the first thing that we're going to do, and we're going to keep the same specifications in terms of the k-fold cross-validation. So we're not going to redo that component of this, that we're not going to do it differently than we did with the lasso regression. So if you remember, we created this object that was called control specs here, or CTRL SPECS. And this is where we specified that we were doing cross-validation, and specifically tenfold cross-validation, that we wanted to save our predictions. And if you were to scroll up in the script, you would find that. Okay, but what we are going to do is we're going to plug it into the train function from the caret package once more, except this time we're going to specify a OLS, ordinary least squares, linear regression model using the LM function. But first we're going to set a seed as we did before. If you recall, this allows us to make sure that we can have reproducible results. So I'm going to do set.seed function. I'm going to put 1985 or 1985 as the sole parenthetical argument here, so I can reproduce what I'm about to do. Okay, so the next thing is that we are going to specify an OLS multiple linear regression model to be estimated using the training data. I'll just put train_df here for short, okay, and tenfold cross-validation. Just to remind ourselves that that's how we're going to be doing this, and we're really not the model is not really being trained per se using tenfold cross-validation. Rather, we're going to be using tenfold cross-validation, get a feel for what is the root mean squared error, or the RMSEA, and the r squared likely to be when we then subject this to new data, whatever model what comes out of this. Okay, so we're going to call this model Model 2, and we'll do so using the left-handed arrow operator. We're going to use that same train function from the caret package that we used before with lasso regression. And the beginning of this function is going to seem pretty similar in terms of the argument structure and specifications. Our outcome is still going to be the r variable, or rather the y variable, which is a lowercase y. We use the tilde symbol, and to the right of the tilde symbol, we enter the predictor variables. We're just going to use the period again because we want to use all other variables in this data frame, so x1 through x36 as our predictor variables, so all other variables except for the outcome variable, which is specified to the left of the tilde. The second argument is just data equals, and we're going to use the training data frame again, so train_df. The third argument, we are going to pre-process the data as we did before with the lasso regression. And so just pre-process with a capital P for process, and then C function, the combined function, and we're just going to specify that we want to both grand mean center, so put center in quotation marks as the first argument within the C function. As the second argument, we're going to scale, which is specifying that we want to standardize the predictor variables as well. So this is pre-processing our predictor variables to grand mean center them and to scale them. And this is to be consistent here with our lasso regression. For lasso regression, it's important to do this. For OLS regression, for our purposes here, not as important, but to have a consistent interpretation in terms of the coefficients, this is how we are going to do it here. Okay, so the next thing is we are going to have the fourth argument be method equals, and in quotation marks, LM for linear models. This is just the LM function that you can use to specify a linear model, an ordinary least squares linear model using R. And here we're just referencing it here. So instead of the GLM net that we use as the method for lasso regression, we're using the LM function here. And then we're going to do TR control, so train control, control with a capital C. We're specifying this argument, and this is where we enter our control specs, similar to what we did with the lasso regression, train function specifications. And here we're just saying that we want to do a k-fold cross-validation. And then finally, this was similar to what we did with the k-fold cross-validation. We're going to say na.action equals na.omit, just so that we'll omit any list-wise any cases or observations that have missing data on any of these variables. And so this is to be consistent with the lasso regression specifications that we did. Okay, so let's go ahead and run all that. We'll wait for the stop sign to cycle through. Pretty quick here, pretty fast to run ordinary least squares linear regression models. Okay, we can use the print function here and take a peek at that model 2 object that we just trained and specified here. You get a little bit of background information. Here's information about you get verification that we did, again, cross-validated tenfold, so tenfold cross-validation here. This is the sample size for each one of the folds, so there's 10 folds, only about 6 of them are presented here. And so what this was doing with the folds, so essentially this is saying that 721 cases were used in the first fold to estimate the model, and then the remaining cases, so it would be 801 minus 721, so those remaining cases were used to test the model, okay, for that fold, and then it cycled through so that each one of the behind the scenes, the 10 subsamples that were specified by the train functions for the tenfold cross-validation, that each one of those served as the validation sample once. Here's the overall RMSE, so the root mean squared error, and here's the R squared value. And so this gives us an idea of overall. So this is probably a good estimate in terms of what we could expect going forward. It's not going to be perfect of when we apply this model that we trained here, model 2, to new fresh data. So that, for example, the test_df data frame, which we'll do eventually, this is essentially what we could expect perhaps with the R squared. And we can also use the summary function from base R. And so summary with model 2 is the sole parenthetical argument there. And we can see, just as you would with a standard linear model here, or OLS linear model, we can see all the regression coefficients as well as their level of significance. And that is one thing that you won't find with lasso regression, is that there has been some movement towards doing statistical significance tests for the specific parameter estimates or regression coefficients for lasso regression, but that's typically less interest because the model is really about prediction, and it's often used with very large sample sizes where our conventional levels of statistical significance are sometimes less of concern, and we're more concerned about effect size. However, and if you remember, lasso regression is really about prediction at the end of the day. Whereas ordinary least squares is often used for understanding, describing, explaining a particular phenomenon of interest and trying to understand how these variables relate to one another. Okay, so here are all the regression coefficients. So here are all the predicted variables and the intercept. And note that unlike lasso regression, every single predictive variable has an associated regression coefficient. None of these are shrunk to 0. Okay? All right, and so now we see here below, and you can get a feel here. So here is the, let's just look at the adjusted R squared here, which is supposed to account for shrinkage. You can see that it's 0.44, okay? But remember up here, we got a taste of what this would look like when actually running the k-fold cross-validation. And what we find here is that it's 0.42 R squared. So we see that this k-fold cross-validation is better able to account for the likely shrinkage that's going to occur. And often this will be more accurate than the adjusted R squared value you'd get down here. Because really all this is right here is just, this is just the final model here is just a standard ordinary least squares multiple linear regression model that's been applied to the entire training data frame, okay? And I can show you and that that's in fact the case very quickly here by just simply, if we just do, I'll just do a quick, I'll just call this M1 for model 1, or actually I'll call it M2, and we'll just consider this to be the equivalent of model 2 here. And I'm going to use the LM function here. If you wonder what I'm doing here, you can check out other tutorials on multiple linear regression and simple linear regression, but I am just going to specify y regressed onto all the other variables, so just as we did before, and then I'm going to specify data equals and train underscore df as the data frame. And I'm not going to center and pre-process things here. We'll focus on the R squared, which will remain the same. And then I am going to summarize the M2 results here. Okay, so if we run that, you will see that down here in our console, that we can just spot check some things here. So let's see what the regression coefficient is for predictor variable x36. It's 0.07009. Okay. Or rather, I'm sorry, we can see right here that, and so that's going to be slightly different there because we did not grand mean and center the variables, the predictor variables here, and pre-process them for the linear model here, the standard OLS linear. But what we will see here is that we do have the same adjusted R squared and multiple R squared value. This is the same model that's been run here. Let's see what the residual standard error is for this model is 0.8192. Here it's 0.8192 for the previous model. Same degrees of freedom and so forth. So we're really talking about the same model has just been estimated here, because that's the final step in this training, is that you just apply in this case, the OLS linear regression model to the entire training data frame, which was 801 observations or cases. But the value here of plugging this in again, doing OLS linear regression within a tenfold or k-fold cross-validation framework, is that we do get a more accurate assessment of how well this model is likely to predict should we give it new data. Okay, because you can see the OLS regression here tends to overestimate the variance explained here. It assumes that it's going to be a little bit higher, about 44%, versus up here it's about 42%. Okay, that might not sound like much, but that's actually a pretty big difference in terms of prediction. All right, so I'm going to delete this part here because it's not really relevant to what we're doing, except just to illustrate that point. But now, okay, moving back to model 2, what we had specified, what if you just want to see, kind of like what we did with the lasso regression, you just want to see the coefficient values themselves? Well, if you just want to reference the coefficient values from the model 2, like up here when we ran summary, we got not only the coefficients, but their statistical significance, standard errors, and so forth, and other model information. Well, if we do model 2, $final model, where model has a capital M, and then finish that up with coefficients, okay, and this will just get us just the coefficients, and let's run that. You'll see here is just a list of the coefficients here. That's exactly what we saw above with our first model up here, or rather the model that we had pre-processed. You'll see the intercept and all the variables. The variable regression coefficients are going to be the same there. Okay. All right, so that step isn't necessarily necessary, but that's just to show you how you could pull that vector if you'd like to. So the next thing that we're going to do is we are going to compare the model performances just from the training data, so from those k-fold cross-validation processes where we resampled the data as part of the k-fold cross-validation, we're going to compare model performances of the k-fold cross-validation on just the training data. So we're just going to see how well those models performed, okay? And by models, I mean model 1 and model 2. So model 1 is our LASSO regression model, model 2 is our OLS linear regression, and we use tenfold cross-validation for both. So what we're going to do is actually create an object. Let's call this the model underscore list object here. And we're going to use the list function from base R, and we're just going to create a list out of all the information that's associated with model 1 object and model 2 object. So in the list function, first argument is just the name of the first model, second argument is the name of the second model, and then we're assigning this to an object that we're just arbitrarily calling model underscore list here. So let's run that. Okay, and the reason we're going to do this is the next thing we're going to do is we are going to use the resamples function. And this resamples function is from the caret package here, and it's going to use as its sole parenthetical argument our model list. And so this is going to essentially pull all the resamples information from the list of models we provided. And you could actually provide a third model here as a third argument if you wanted to compare three different models or 4 models. You could keep on going. And so this will allow us to compare the model performance in terms of RMSE, root mean squared error, R squared, mean absolute error, that kind of thing. And we want to assign this using the left-handed arrow, the output of this, to an object that then we can summarize. So let's just call this object resamp. Okay, so fairly arbitrary, but I'll just call it that. Final step, just summarize that object, get the summary results from the object that we call resamp, and let's run all this together. Okay, so now you can see down in our console here, we can see that we summarized the resampling information from model 1, model 2. So the number of resamples is 10, which means 10 folds here for our k-fold cross-validations. We won't really interpret the mean absolute error here, or the MAE, but we will skip down to RMSE and R squared. And really what we're interested in, first off, is just the mean. Okay, so remember with RMSE, root mean squared error, we want that to be lower. So what's interesting here, you'll see right off the bat, is the LASSO regression has lower root mean square error than the OLS linear regression model. So that's what you would kind of expect here. And the LASSO regression performing better from a prediction standpoint. And then with R squared, we see that the R squared, we want this value to be higher. We see that R squared is about 44% for the model, the LASSO regression final model, and it's about 42% variance explained for the OLS linear regression model. And you can get a sense of the range too of these estimates by looking at the minimum value, the first quartile, the third quartile, the median, and so forth as well. Okay, so that just lets you know how well the models performed with the k-fold cross-validation. But really, what we ultimately are trying to get to here is that we would like to see how well the models are actually going to perform, and we can think about it from a statistically significant standpoint. So here we just describe the differences, but we can ask, are these statistically significant differences in this particular case? Well, there is a way that we can do this, where we can compare the models, the model 1 and model 2 in this case, using a paired samples, or which is another way of saying a one sample t-test, same thing. And we can use the compare underscore models function from the caret package. And as the first argument, we can put in model 1, second argument, we can put in model 2, and then we can specify the metric we want to compare the models on. And so let's do RMSE. So metric, let's see whether or not these two models are significantly different in terms of the root mean squared error. So RMSE, all caps. And let's run this. All right, so here you can see we get a t-test here with degrees of freedom 9. So this is just 10 resamples or 10 folds minus 1 to calculate the degrees of freedom for this one sample t-test, which is again just a paired samples t-test in reality, or another way of saying that. and the p-value is non-significant. So here we don't find that the above means that we saw for root mean squared error, these two means, they're not statistically significantly different from one another. Granted, we only have essentially a sample size of 10 here because we had 10 folds, okay? So we might not have too much statistical power here. Now let's do the same thing. Let's copy and paste this, but now let's look at the metric of r squared and see whether or not those are similar, statistically different from each other. So r squared. Okay, so specify that as your metric and run. Same thing, it is not statistically significant, okay? So that can be useful, although I'd say that most of the time, this one sample t-test or paired samples t-test that you can use with the compare underscore models function here, it's going to be most informative when you have, if you have a lot of data where you might be able to do like 15 or 20 fold cross-validation. When you get down to 10-fold cross-validation, that's a pretty small sample that we're throwing in here in terms of the number of resamples or folds. Okay? All right, so the next thing that we're going to do is let's actually see how well the OLS linear regression model performed. Okay, so let's predict the outcome using the model from the training data based on test data, okay? And so this would be very similar to what we did with the LASSO regression model, except now I'm gonna call this object predictions 2 instead of predictions 1 that I'm about to create here. And we'll use that same predict function from base R, and the first argument is model 2, and then to specify the model that we want to apply to the new data. And then the second argument is what is the new data? New data equals, it's our test underscore df data frame. So that was the holdout data that we did not train either model on, either the LASSO regression model or the OLS linear regression model. Okay, so we want to run that. Okay, so we created that object. The next thing we can assess is model performance. And so how do we do that? Well, if you remember before, I created an object called mod1perf for the LASSO regression. Let's call this mod2perf. Okay, and so we're going to use a very similar process. In fact, what I'm going to do is just to save some time here, I'm going to go all the way up. This is like the last step we did with the LASSO regression here. I'm just going to copy this chunk here, paste it here. And all I'm going to change here is instead of predictions 1, we're referencing predictions 2. So this is for our OLS linear regression model, so our second model. Just changing those values. All else stays the same. We're just going to get a data frame object called mod2 performance that has our RMSEA and r squared values. So these are going to be the two variables of interest. So let's run that. Okay. And then the final step, we can just print that, or we could just highlight this here and run that, but let's just do mod2perf is this little argument in the base R print function. And here is the information in terms of the prediction accuracy of our r squared, or of our second model, which is the OLS linear regression model. So if you note here, so we go back up to these results here. So remember, model 2 is our OLS linear regression model. Here we can see the RMSE for the OLS linear regression model is about 0.837, and the r squared is about 0.4239. Let's see how well this model actually performs when you give it new data. Well, you can see that the RMSE goes up by like 0.02 or so, and the r squared goes down by like 0.02, 0.03 or so. So this suggests that there was shrinkage that occurred when we used the OLS linear regression and applied it to new data. It didn't predict as well as maybe we would have expected it to. Okay, so the next thing that we want to do is let's actually see how well the predictions for our OLS linear regression model compare to our LASSO regression model in terms of the performance metrics of RMSE and r squared. Okay, and so how to do that? We are going to come up here and let's just make a note that we are going to compare model 1, so LASSO regression, and model 2, predictive performance based on the test data, so the holdout data. Okay, so we're going to compare essentially those predictions and the predictive accuracy. And so what we're going to do is actually create a matrix. This is going to be a little bit more of a cumbersome process, but it's a nice way of kind of synthesizing and pulling these all into what will end up being a single table. And so let's call this initial matrix, let's call it comp2 here. We can just call it comp, okay? We don't have a comp1, so let's just call it comp. And we'll use the matrix function from base R. And what we're going to do first is we are going to specify as the first argument what are the components or the elements of this matrix. And so we're going to do first the model 1 performance RMSE, and then the second is going to be the R squared. And so we're actually going to reference the mod 1 performance data frame from the LASSO regression and the mod 2 performance data frame object we created. So we'll start with the mod 1. So remember, it's mod 1 perf $ RMSE. So all this is doing, remember we created, this is for the LASSO regression, this is what we created here. Now we're just referencing these in this matrix and creating, so we can ultimately create a table out of this. Okay, so first we're starting with mod 1 performance RMSE. The second argument is just going to be mod 1 perf and R squared. Okay, and then I'm going to do a return here just to signal that we are going to, the next row is going to correspond to the model 2 performance or mod 2 perf, which was our OLS linear regression model, RMSE, and this is what we just created up above here. We're referencing the variables in this data frame here, so mod 2. This is all we're referencing here. So we'll start with RMSE, and I'll just copy the beginning of this and replace this last one with R squared. Okay. All right, so I'm going to come outside of that parentheses there to close out the C function. And now we're going to go down to the second argument for the matrix function. And the second argument is going to be we're going to specify the number of columns. So in call equals 2. And this just says that we have 2 columns here for our matrix. And here I kind of noted that with how I laid out the elements of this matrix here. So the 2 columns are going to end up being that we have 1 column for RMSE, 1 column for R squared. Okay. And then I will do by row equals true. And this is just saying that we are going to focus on this, that we're focused on this matrix in terms of it's by rows that we're organizing these data. Okay. So RMSE, so the first row is going to be model 1, the second row is going to be model 2, in other words. Okay. So let's run that and create that matrix object. Okay, you can peek at it right here if you click on it in your global environment. This is the matrix object. You can see it doesn't have any labels yet though, but it has the raw elements there. So how do we make it into something that's a little bit more visually compelling and informative? Let's name the columns and rows of the comp matrix object. Okay, and so we're just going to use the call names function from base R and put the name of that comp table we just created as a sole parenthetical argument. And then to the right of it, we're going to use the left-handed arrow, and we are going to use the C function to specify in order the names of those columns, which is RMSE. That's what we're going to name the first one since it'll have the root mean squared residuals. So here's the first column, here's this second column. The second one is, let's just call it R squared. Or I like calling R squared, I like dropping the D, but okay, so now we have column names here. If we go back to our comp matrix, you'll see now we have column names there. Okay, so now we need row names. So we want to say that the rows are model 1, model 2. Okay, so we'll use the row names function from base R, and to the right of that function, and so we're using row names, and again putting comp, this matrix object, as a sole parenthetical argument. And to the right of this left-handed arrow, we are going to specify using the C function from base R, what do we want those rows to be in order? Well, the first one, let's be specific here. Let's not call it model 1. Let's call it LASSO regression. And then the second one, let's call it OLS multiple linear regression, or OLS MLR. Okay, so let's run that. Now if we look at our comp object again, okay, this is a little bit more informative. And then we can actually make it into a traditional table object. by, let's overwrite the existing name, the matrix object, and convert it to a table by doing as table. And the sole parenthetical argument, just put the name of the comp object we've been working on. So run that. So now it is a table, okay? And then finally, let's round, make sure that it's only to 2 places after the decimal, just for interpretation reasons. So let's do comp. So we'll round the comp table object, and as a second argument, the number of decimal places after the decimal point. Click run. Okay, so here's our table here. So we can compare how well did the RMSE do, or how well did the lasso regression model do compared to the OLS linear regression model when it came to predicting the outcome of interest, which in this case was lowercase y, whatever variable that represents. And remember, we want RMSE to be lower. And so here you can see the lasso regression, when given new data, it was slightly less error in prediction than the OLS linear regression model. So that's, in terms of prediction, lasso regression outperformed there. And then we also see that the R squared is higher, which is good, more variance explained in that outcome Y by the lasso regression model than the OLS multiple linear regression model when we gave it the new data from the test_df data frame. Okay, in some cases, so this isn't a huge dramatic departure, but you can imagine over time that even a 1% increase in R squared via lasso regression could be quite valuable, especially if you consider that at scale. And also sometimes you'll see much bigger differences, especially if you have a lot more variables. Here we had 36 predictor variables. If you had 100, you might see some very dramatically different or very notably different R squared and RMSE values here. Okay. But still, this illustrates the point that lasso regression tends to be good at optimizing prediction here, and tends to reduce shrinkage when the model is applied to fresh new data. All right, so this wraps up part 2 of the lasso regression in R tutorial. This part was obviously just to compare lasso regression to ordinary least squares linear multiple linear regression model, which is just the conventional traditional type of regression when we have a continuous outcome variable like we do here. And again, we got to see via this model comparison that the lasso regression tends to lead to better predictive models, more predictive models with greater predictive accuracy. Thank you very much.